Last time we talked about spheres, ellipsoids, and paraboloids, where the paraboloids took in a couple of forms, elliptical and hyperbolic. So now we're going to talk about the last types of surfaces, the quartic surfaces called hyperboloids. And then we're going to squeeze in the idea of cones as well. And we'll try to take better shots of pictures of things. And for that, I'm going to go back to using graphing calculator on this computer. So the last case that's left is when all of the variables are squared. When you have x is squared, the y is squared, and the z is squared, and then it's not all the same sign. It's not all pluses and then equal to something else. You know how if this is all plus and this is equal to a number, then it's like a sphere or an ellipsoid. So what I want to do now is I want to take a look at the case where it's not all the same sign. And we'll start by looking at this when one of them is a negative sign. Let's make the z negative for now. What we did last time was we took a look at cross sections. We took a look at what happens on the coordinate planes by letting x or y or z equal to 0 and seeing what kind of shapes we have. And then we went further and let z equal to a variety of different numbers and see what happens. So let's take the same approach here. Let's start with the xz intercept. I forgot what color I was using for that, but let's let xz plane. That's when y is equal to 0. So let's see how this thing looks like when y is equal to 0. Oops, z. Is that? Okay, so when y is equal to 0, I have x squared minus z squared is equal to 1, which is a what? That's a hyperbola. So we went through the conic sections back in Chapter 10 so that we can get familiar with these shapes. And so I'm hoping that, when you see equations of only two variables, that you should be able to figure those out, what kind of shapes those are. So this is a hyperbola, and it looks like the z is negative, the x is positive. So I'm going to, it looks like on the xz plane, if I were to look at this on the xz plane point of view, if my z was equal to 0, that's the x-axis, my z was equal to 0, I would be hitting, x is going to be hitting at positive and negative 1. And if x was equal to 0, that would be the z-axis. If x was equal to 0, then negative z squared is never going to be equal to positive 1. So I know that my hyperbola is going to be opening up sideways like that. That's on the xz plane. So in an attempt to draw this in 3D, I would get a little trace . It might look like that. Hitting when x is equal to positive and negative 1, it'll be opening up sideways like that. So now let's see what happens when x is equal to 0. And for that, I'll be looking at the yz plane. So when x is equal to 0, I have y squared minus z squared is equal to 1. And it looks like it's going to be almost the same scenario, except I'll change my axes. So when I draw this in this graph, I would be opening up this way. Okay? So the other part that's kind of revealing would be what happens on the xy plane and any other levels that are parallel to the xy plane. So on the coordinate plane, xy plane, when z is equal to 0, I would get z is equal to 0. I get x squared plus y squared plus 0 is equal to 1. So that's a circle. Okay? And we'll try other levels, like when z is equal to positive 1. I have x squared plus y squared minus 1 is equal to 1. So that's x squared plus y squared is equal to 2. That would be a circle slightly larger than 1. And then maybe do one more, say when z is equal to negative 1. Get x squared plus y squared minus 1. Negative 1 squared is positive 1. So that's going to give me the same circle as I got down here, the same radius. So it looks like it's going to be a, whatever that, hyperboloid. It's going to be a hyperboloid, and it looks like it's a hyperboloid that has one sheet. That's made of one surface, I guess is the way to do it. Like a tire rim, yeah. If you stop, but technically it goes on forever. But yeah, it's like a tire rim. So that's what you have. Okay. Any questions? All right, let's start our drawing business over here. X squared plus y squared minus z squared equals 1.
And when we change the value of 1, is that just distinguishing how big that smaller inner circle is?
Yeah.
I.e. the xy intercepts?
Yeah. So if I draw another one, let's say where this is equal to 2. Looks like it's going to be a little bit wider than the other one. Okay? All right. Now, oops. Just want to take a picture. Now when I start off with this equation, I kind of just said, oh, what if we make, they're not all positive. The x plus y plus z, it's not all positive, so I made one of them negative. So now another question would be, what if we made not one of them negative, but two of them negative? So what if we take this equation And instead of making one of them negative, maybe make two of them negative. So I'm going to put a negative in front of the x squared and the y squared, and then make the z squared positive. Because the key, remember, is that they're not all the same sign. So the question is, what would happen here? Well, let's see what would happen. Well, first of all, I guess a good question is, do we even still have a graph here? I don't know. But if we go through the process of what we did before, let's look at the coordinate plane intersections, and then we'll look at horizontal cuts and intersections, then maybe we might get somewhere. So let's what did I do last time? I think I did y is equal to 0. On the xz plane, y is equal to 0, I have negative x squared plus z squared is equal to 1. What is this? What kind of equation is this? It's another hyperbola. Did a negative sign in the front throw you off? If you switch to order, you get z squared minus x squared, and it will be the same thing, right? So so this will be a hyperbola, but this time this hyperbola looks like it might open up not sideways but going up and down. So if this is the x and z axes, it looks like this will open up along the z. So our graph looks like it'll open up along the z-axis like this. I should have drawn this kind of slanted. All right. The next one is if we let x equal to 0, we're kind of get the something really similar. Another hyperbola on the yz, opening up along the z-axis again. So this time it will be like this. So already that looks a little different from what we saw before, right? Now this is where things really get clearer or more messed up. I don't know. It depends on how you look at it. Let's see what happens when z is equal to 0. Let's see what happens when this thing intersects the xy plane. You have negative x squared minus y squared minus plus 0 is equal to 1. So there's an issue here. This is positive 1. The squares, whether the x and the y are positive, they're going to be squared, so the quantities themselves are going to be positive, but then there's a negative in front of both of them. So we have a negative number equal to 1, which is never going to happen. So there's no solution here. That means this surface doesn't cross the xy plane. Does that make sense? Surface does not cross the xy plane. Let's try z is equal to 1, if that gets us anything better. I have negative x squared minus y squared plus 1 is equal to 1. And if I bring the 1 over to the other side, or I suppose I can bring the x squared and y squared over to the other side and the 1 to the left side, 1 minus 1 is 0. So I got x squared plus y squared is equal to 0. Do you remember what that was? 0, 0, right? It would be 0 for x and 0 for y. but the z is equal to 1 because that's what we set it as. So there's one point where that plane is going to touch that graph. So you're are you seeing what's happening? Let's go up one more. Z is equal to 2. You get negative x squared minus y squared plus z squared is equal to 2. Oops, no, let's try that again. 2 squared is 4 and is equal to 1. That's the equation. So I'll bring the x squared plus y squared on the right-hand side so that it's positive, and then I'll bring the 1 over to the other side so that we got 4 minus 1 is 3. So I have a circle, a radius square root of 3 at the z is equal to 2 level. So at the z is equal to 2 level, I have a circle, a radius 3, and then that's my surface, at least the top part. And since z is squared, whatever happens in the top part is probably going to be the same thing that happens in the bottom part. So it looks like paraboloids going upward. But they're not really paraboloids, really. They're hyperbolas if you take the cross-sectional cuts on them, right? Because that's what we discovered here. So instead of saying there are 2 paraboloids, they're actually hyperboloids. But this time, these hyperboloids are separate sheets. You need 2 sheets to cover these hyperboloids. So they're called hyperboloids of 2 sheets. And would it be fair to say that a hyperboloid of 2 sheets, if you take a look at this equation, instead of putting a negative x squared minus y squared plus z squared is equal to positive 1, I can just say positive x squared plus y squared minus z squared is equal to negative 1. If we take a look at the graph of that, you'll see that now it's hyperboloids going across. All right? And then if we change those values from -1 to -2 or something like that, then you'll see these hyperboloids just kind of stacking themselves up. All right. So we have hyperboloids of 1 sheet and a hyperboloid of 2 sheets. And it looks like the connection between them is just looking at the values on the other side. We usually like to see them as 1 on the other side to help us figure out like how the shape of those things would look like. In general, this is how it's going to look like. But we are going from negative numbers. If you put negative numbers here, then we got 2 sheets. If you put positive numbers there, you get 1 sheet. So what's between a positive and a negative number? 0. What do you think would happen if we put 0 here for the right-hand side? You think it'll be a dot? Any other guesses? Ideas? You saw a cone up there earlier. I did write cone. So it must be a cone. Usually cones are seen a little bit differently. Instead of writing the equation like this, they usually put the z on the other side. And if you don't have an extra constant laying around, usually you make the two of the variables positive and you get the other one on the other side. And then you have something like this. So what is this? We think about if we go through the same process, and we should go through the same process when y is equal to 0, I have z squared is equal to x squared, which is that x graph that we saw before, right? It's like if you take the square root, you got z is equal to plus and minus x, and so that's the z is equal to positive x, z is equal to negative x. So those are two lines, actually. And then similarly, when x is equal to 0, you got z is equal to y squared, or z squared is equal to y squared. And again, that is an x on the yz plane. So now if you let z is equal to 0, you're going to get 0 is equal to x squared plus y squared, which we know of to be a dot. X is equal to 0, y is equal to 0, and in this case z is equal to 0. When z is equal to 1, you get 1 is equal to x squared plus y squared, which you know to be a circle, etc. So if you imagine how this thing might look like using these pieces of information that we are gathering, you got that x over here, you got another x over here, you got a dot over here, and you got circles going up there. It's what? No. Oh, what? It's like, well, it's not a curved hourglass, but it's actually a cone. So it actually makes a point, a sharp point down here. All right, so this is your cone. And that would be nice to see over here as well. If you take a look at the graphing calculator. So that's just a cone. And sometimes the cones can be described differently in different ways. If you look at this cone, you'll see that this is not just a cone, it's two cones, right? If, say, I just want the top cone, what can I do? Y? Z? Z is equal. So I can put z is greater than 0 here, but we can also write something a little bit different. Right, z is equal to, if we take z and bring it to the other side, right, which is what I have over here, and then take the square root. So if I take the square root, then there's a positive square root and a negative square root. So if I just care about the positive square root, then it's just looking at the top part of the cone. And if I want to just look at the negative square root, then it's just going to take the negative part of the cone. All right? So that's like the circle. If you take this, y is equal to the square root of 1 minus x squared, that's the top part of the circle. And to capture the bottom part, then you would get y is equal to negative that. Okay? So there's this cool animation idea that connects the hyperboloids, it turns out. And if we just take one of these equations and make this into a parameter A, and we'll let A be a slider like we've done before, so we can animate. We can start off with a hyperboloid of 2 sheets, and then move this until it becomes a cone, and then it becomes a hyperboloid of 1 sheet. It's pretty cool, huh? Okay. It turns out the paraboloids have that same interesting property. This is a paraboloid that we know of, and then if we shift the paraboloid to make it look more and more like an ellipsoid, and then at some point it's going to break and become a saddle, create the same sort of animation. All right, so now once you know those basic surfaces, the rest of this will just become variations on twisting them. If you take the hyperboloid that we were just looking at, some of the variations for the hyperboloid, you just divide it by some values, and then it would look like some hyperboloids that look like the hyperbola formula in the conic sections. Then it'll just change the shape a little bit. And if you switch the variables z and x, then it'll be a sideways hyperboloid or paraboloid or whatever else you're looking at. So you can make sideways cones as well by doing these things. This is a sheet that I stole from that video the other day, and so now it's in the notes. If you want to take a close look at it, can't really see it. You can take a look at the notes that I have here. But going sideways, if I was interested in having a hyperboloid go sideways, I simply have to switch the orientation of where the x and the z, or the y and the z is going to go. So just do one more graph. So put the negative in front of the x instead, and then make the other two positive. So this looks like the same thing, except the signs of y and z are the same, and so the x is different. So you would imagine this is a hyperboloid of 2 sheets, 1 sheet. And then this is going to open up along the x instead of the z. So how many say 1 sheet? How many say 2 sheets? I think it's 1. Yeah, so there's 1 negative, and then the constant's positive on the other side. So this is a hyperboloid of 1 sheet, and it's opening up along the x-axis. All right? Okay, any questions? So, trying to learn about this by looking at pictures and doing homework and stuff like that may be effective, but I think the more effective way to try to get to know these surfaces is to graph them yourselves. And if you're able to buy this particular program, then it's going to be really easy. But if you can't buy this program, I've told you about that site. Oh, I didn't want to use that. I told you about that site or the 3D calc plotter that you can run on your computer, and it's free. And what we've been dealing with are called implicit functions. So with the implicit functions, because they're x and y's and z's put together in one side of the equation, and we're not really solving for one particular variable by itself, because we're not doing that, you can't write it as a regular function that they have here in the front page, wherever the front page is. I said run. I think you can download it too on your computer so that you don't have to be connected. I'd like to think that this is easy to deal with. And it is. A few things to look out for is this button that says clear the graphs. And this is defaulted to be checked off, and this is the default graph that it draws, which is a nice graph. But that's not what we're studying right now. That's going to be in Chapter 14, so we'll take a look at that later, these types of functions. But the kind of graph we're looking at are from the quadratic surfaces, and so for that you need to hit graph, add an implicit surface, and this will open up a place for you to type in an implicit surface. Already I think they look like they have a function here. X squared minus y squared plus z squared is equal to 1. What kind of hyperboloid is this? 1 or 2 sheets? It's a hyperboloid of 1 sheet, and it's opening up on the x, y, or z. On the y, that's the one that's negative, right? So let's graph that, and it looks like it is, in fact, a hyperboloid of 1 sheet opening up along the y-axis. And if you, like, maybe throw a negative sign here, then it becomes a hyperboloid of 2 sheets. And so it's up to you to actually dive into this and play around with it, because in the future we're going to be talking about surfaces, and I'm going to say, oh, I want an equation of a cone, and it's up to you to try to pull that out of your something. Yeah.
What if we give some of them coefficients?
Oh yeah, so if we give some of them coefficients, put a 2 here or something like that, then your cross sections that we were taking earlier, the cross sections wouldn't be circles, they would be ellipses. And so those are the differences. And so if you take a look at the samples that they have here, they all have kind of like the ellipse and the hyperbolas that we saw in the conic sections. They have divided by a squared, divided by b squared, divided by c squared in this case, because there's a z component. Then that's a big difference between them. Okay? It would look elliptical instead of circular. Anything else? All right, good. So that's your rundown. I can keep talking about it and amuse myself, and you guys can just keep watching and not learning anything, or you can actually try it yourselves. And that's, I'll go with the second one. Because now we could talk about the next section, chapter 13.1, 13.2. And that will lead us to parametric curves. We've already talked about parametric curves. Why are we talking about it again? Because now we get to bring it up to 3 dimensions. So parametric curves in 3D. We have already seen parametric curves in 2 dimensions. We have actually seen a parametric curve in 3D already, right? You know what I'm talking about? What?
4D?
No. What's a parametric curve in 3D that you guys have seen already that we've been talking about? No, Pringle's a surface. What? R equals R naught VT. Now, the word curve here is a general term for a one-dimensional object. And just because Diana said an equation of a line doesn't mean that that's not a curve. Technically, that is a curve. So, yes, we've seen R is equal to R naught plus T times V. So this is a line. But when we talk about lines in 3D, that's the same thing as talking about curves in 3D. Actually, when we talk about lines in 2D, technically that's a curve also. So lines are curves when we're looking at it in 3-dimensional. So parametric form is generally what we want to see, and so we normally break this down into, I think it was x naught plus v1t, comma, y naught plus v2t, comma, z naught plus v3t, where x naught, y naught, z naught is your point, and then your v1, v2, v3 are the components of the direction. And not like it has to be said, but just to be explicit about it, these are your x, your y, and your z functions. They're functions of t. In fact, maybe if we write it like this, y of t, z of t, x of t, then it would be clear that they are in fact functions of t. So by now, I hope you know how to find equations of lines. Say I had 2 points. So say I had 2 points in 3 dimensions. Why don't you guys yell out some numbers? All right, we have 2 points in space. I want to find a line containing these 2 points. Would you know how to do that? What do we need for an equation of a line? A point and a what? And a direction, right? So I have a point and a direction. If I have a point and a direction, I just plug it into this formula. I have 2 points, but I don't have a direction. What do I do? Find a direction vector. How do you find a direction vector? Head minus tail. It doesn't really matter which way I'm going, so let me just randomly pick my direction vector to be going from this point to this point. What is this vector going to be? We just subtract head minus tail, and then we pick any of these points. We probably should pick the first one, but we could pick the second one just as well, and then we will get an equation, a parametric equation of a line. So let's pick 8, 6, 3 plus t times 1, negative 8, 8. And then just to be flexible, I'll write it as an x equal y equals z equals, so we can see it in parametric form. Actually, let me write it x of t equals 8 plus t, y of t equals 6 minus 8t, and z of t equals 3 plus 8t. So that's my parametric equation. I can write it like this in 3 equations. I can write it like this in 1 equation, in 1 vector with 3 components, or I can write it like this in pure vector form. Do you ever wonder what that looks like? What does that mean? What does t do? T do. T gives you the parameter of when you plot it. Okay? So let's see. I think I made one up earlier. Where's my... vector grapher. This is in 2D or 3D? Ah, this is in 2D. Let's make one up in 3D. Let's do a vector grapher. I don't know why I'm doing this. I'm just wasting time.
Well, wouldn't we just be plotting those 2 equations and then having t on the sliders?
Yeah, well, the thing is that you would draw it in 3 dimensions. Yeah, I don't have time for this. All right, well, let me throw something at you here and have you guys think about this. So anytime you have an x of t, y of t, z of t defined as a function of t, you're going to have some sort of curve in space. Now I want you to make sure that that's distinguishable from the surfaces that we're looking at. Surfaces are different. Surfaces are not the same thing as curves. So let's do an x of t and y of t that you're familiar with. And you know what this does, right? But let me throw a z of t here that does something else. Let's do a 1/2 t. Now imagine what's going on in 2 dimensions, first of all, because I made this simple enough for you to try to imagine what's happening in 2 dimensions. And we don't have to stop at pi. We can go on forever in both directions, negative and then past 2 pi. But the z is acting as something that does something to your z-axis. I don't know if that made any sense, but the z is doing something else to this point that you're plotting. So imagine your t is equal to 0, you're at some point, and then as t gets larger and larger, your x and y is drawing a circle. And as you're drawing the circle, your z, which is your height, is changing, right? In this case, it's going up. So what do you think this is going to look like? What? What? Close. The staircases? So I have too many things open here. It's a what? That doesn't give me much. Let's go from negative 10 to 10. And I'm going to squeeze my z-axis a little bit to capture more of this. Anybody? Before I press go? It's okay to be wrong. It's okay to be wrong when you're yelling out answers than be wrong on your exams, right? So close, it's a cylinder. It's on the cylinder. If we were to draw a cylinder, it would be on the cylinder. But since it's a curve, a cylinder is a surface. Since it's a curve, it's something else, right? It's not, you wouldn't describe a curve as a cylinder because a cylinder is a surface. So in this case, it's a spring. It looks like a spring. Okay? So I think the task in 13.1 is for you to try to identify how things would look like. I'm just going to stick with some easy problems here. Oh, maybe take a picture of the spring since we have it. Now let me try something else on you. X is equal to cosine t, y is equal to sine t, z is equal to sine, let's say, 8t. So imagine your x and y again. You have a vector x and y that's still going around in a circle. As you're going around in a circle, what do you think is happening to the z-axis? Okay, hurry up because I need to go.
It's going to fluctuate how quickly it
Sine curve wrapped around a circle. That's a good way to describe it. Is that what you guys had in mind? What did you have in mind? Did you have this in mind or did you have this in mind? I'm just kidding. Oh, what? All right, so these are simple ones where the sine and cosine are in x and y, so you know that you're just moving around a circle. There are a little bit more complicated ones in that section where they do different things, but you have to try to imagine what's happening with the x, the y, and the z at the same time and see what kinds of things that these things might draw out. All right? So there's some homework due. I heard there was a lot of homework due. All right, good luck. Go get them.